Sorry, what?
Yeah, that's what.
And wants real estate.
Yeah. They go pretty hard. Like everything. It's good though. Very heavy. That'll just knock you out.
Yeah.
Should I just start or?
Hello everyone, welcome back. Professor Lukin will continue with his third lecture.
All right, so let me just begin by kind of recapping what I was talking about yesterday, so it's somehow barely visible here. But so I talked about our experiments involving Rydberg quantum simulators based on neutral atom arrays, and I told about how actually how we assemble quantum matter atom by atom. I talked about sort of experimental ingredients. But also I then described how we can implement spin models with kind of tunable interactions, tunable couplings, and use it to explore different types of phase transitions. And so in the second lecture, I talked about probing quantum dynamics using the system, in particular observing quantum Kibble-Zurich mechanism. And I also talked about this concept of quantum scars. So I realized at the end that a lot of these kind of necessary ingredients which kind of go into that is something that you will hear in other lectures. And so, for example, Marcos yesterday already kind of introduced these concepts of chaotic and kind of integrable systems. So these are very much central concepts that go into kind of observations into interpretation of this kind of experiments. So, for example, quantum scars is a kind of this phenomenon which possibly does not fall into any of these kind of categories. So it occurs in a system which has formalizing kind of bulk states, but it has kind of a special band of states. And kind of understanding that, understanding why this occurs, understanding the necessary conditions is kind of an active research topic. And basically I hope you kind of now see the connection between these kind of different directions. Does that make sense? Or do we still have questions about yesterday's lectures? Okay, so today's topic, today's subject of my lecture will be also a little bit in the same spirit. So I will be talking about the so-called time crystalline order, and I will describe what it is, and I will tell you about a physical system in which we observed this effect. This is strongly interacting defect centers, basically spins associated with defect centers in diamond. And I'll tell you how we observed this experiment and how we actually, what's our current understanding of these observations. But the central feature of this lecture will be very much kind of a connection between these discrete time crystals and this concept of quantum thermalization that Markus has talked about. However, I should tell you that some of the things which I'll be talking about will be related to things like many body localizations, and this is what you will hear about in Rahul's lecture. So view it as a kind of experimental teaser, kind of a preview of something that you will learn in depth later this week, today and tomorrow. Okay, so let me now focus on this time crystal. So I talked yesterday. I talked yesterday about kind of the idea of trying to explore Hilbert space, in particular far away from equilibrium, looking for new stable states. So kind of quantum scars is perhaps an example of such states. But there is another example, and that is this famous so-called time crystal. So what the time crystal is kind of a state which features spontaneous breaking of time translation symmetry. So what is it all about? So basically, if you have a Hamiltonian which has spatial translation symmetry, then the kinds of phases of matter it can have as a ground or some thermal state could be either a disordered phase, like for example liquid or gas, or the ordered phase in which this kind of spatial translation symmetry is spontaneously broken, right? So the idea here is if you have a crystal, if you have one atom, if you know the position of one atom, then you in principle know the position of all of other atoms, like kind of like what you've seen yesterday in the example of this kind of Rydberg simulators. And so basically what will happen is that if you plot, for example, another parameter, kind of a correlation function, then what you will see is that you will see this kind of, it will be periodic in space. So the idea of time crystal is, or sort of the hope, or kind of the concept of time crystal is to have the states in which basically the position here will be replaced in time. So that will be kind of a structure which is periodic in time. So if you know the value of the order parameter at certain time, then a long time later, after a certain period, it should come back. And one thing that I'd like to emphasize is that the key property of the crystals is rigidity. So, for example, you could say, well, is like the fact that every morning the sun is rising, is it a kind of a time crystal? Well, it's clearly a periodic phenomena, but this would not quantify kind of as a time crystal, because in some way this is not rigid. If like a big asteroid hits the Earth, right, the position of the Earth changes, right, the timing will change, right, and that's kind of means that this kind of rigidity which is present, for example, in special crystals where you perturb, you try to kind of move them. Move the atoms, the interactions between atoms hold them in place. So basically, in looking for this time crystalline response, we will also look for this kind of periodic phenomena, which in some sense are robust, right? Will be robust with respect to perturbations. So the concept of this time crystal was originally proposed by Frank Wilczek, and I guess the kind of the physics of what motivated him is that, well, time and space are in some sense equivalent, especially kind of in relativistic situations. So then, if you have spatial crystals, why shouldn't you have also this kind of corresponding phenomena in time? And he even tried to kind of cook up some model for this time crystal, and the kind of things that he was thinking about is essentially, suppose you have a current in the ring and there is a flux penetrating the ring, and then you add strong interactions between the particles, and can be either attractive interactions or repulsive interactions. And then what will happen is that in one case the particles will bunch, and another one kind of repel each other. And if this kind of current will go on forever, right, then we'll create a structure which is periodic in time, right? So, I mean, this is in principle, quite plausible and reasonable idea, but it kind of does not, smell right. It smells like kind of perpetuum mobile a little bit, And once his paper was published, people started seriously thinking about whether it's possible to have something like this, and actually very soon it was proven mathematically that this kind of first of this specific case, doesn't work out, because the state would not be stable. In fact, quite generally, if you have kind of Hamiltonians with kind of reasonably local interactions, and in particular, if you're now asking the question either about the ground state or a system in thermal equilibrium, this time crystalline order will not be, will not exist. It will be unstable. And so at this point, you could say, okay, that's kind of the end of the story. There is nothing you can do. You cannot fool nature. But actually, it turns out that if you start relaxing some of these assumptions here, you can actually have a stable time crystalline order. So specifically, these kind of general arguments do not apply to systems which are out of equilibrium, which are taken out of equilibrium. For example, system which you can periodically drive by applying some external control field, which you drive out of equilibrium, will not be subject to these theorems which have been proved. And of course, what you also need, for this time crystalline response to make it kind of rigid and robust, you need strong interactions. And so, basically, if you have a system which is strongly interacting but do not undergo formalization, then these arguments also don't apply. And so, okay, I mean, the fact that you can drive the system out of equilibrium doesn't surprise anyone. So the second kind of condition is actually is a little bit unusual, but there are states known which satisfy these conditions, such as, for example, the states in the systems in the many-body localized states. And that's the kind of things that Rahul will be actually talking about in depth, but let's for a moment assume that such states exist. So basically, what it means is that in principle, if you start thinking about systems of this kind, it is plausible, at least mathematically, that you can create a stable time crystalline ordered state. And so this kind of gave rise to the kind of idea of discrete time crystals, and this idea actually originated here at Princeton, and particularly Vetica was a student at the time, and now as a postdoc at Harvard was one of the leaders kind of in developing this idea theoretically. See, I stick with my promise that everything I talk about has a connection to Princeton theoretical physics, of various generations actually. So there will be more examples later today. Okay, so so actually, in fact, about a year ago, two years ago, two experiments actually demonstrated this kind of idea experimentally. So one involving was a Chris Monroe's experiment, who realized this time crystalline order with 10 trapped ions. And actually, I will tell about the other experiment, where we use large ensemble of spin, like 1 million of spins in black time. So what is this discrete time crystal? So basically, there is this keyword discrete. So it's it does not break continuous time translation symmetry, but it breaks discrete time translation symmetry for a system which is driven by the pulses. So specifically, suppose that you have a quantum system which undergoes the unitary evolution, where unitary evolution consists of this kind of blocks or fundamental units. So these fundamental units might themselves involve application of different types of Hamiltonians, but let's call this unitary U sub f. And so basically, the periodically driven system means that you basically apply this unitary periodically, like with some period t, right? You just keep applying it. And normally, you would think that the system should respond with the same theory, with the same period, but actually, it's not always the case. So, in fact, in this discrete time crystalline order, what it will do, it will respond with some period which will be a multiple of this fundamental period, nt, right? And that's kind of breaking discrete time translation symmetry, right? So usually, you think that it will respond to each of these unitaries kind of in the same way, but it actually does not. If it does not do it, that's when you break discrete time translation symmetry. And so basically, what I will explain you, it's actually interactions are very important to stabilize this kind of order. And at the end, the key features of these two key features of this kind of discrete time crystalline order will be robustness to kind of imperfections. For example, if our driving kind of is not perfect, these interactions will still stabilize this state. So it will not be just like a perfect oscillator, which, so long as you drive it perfectly, it will kind of respond perfectly. It should have some, kind of intrinsic robustness. And in addition, the strong interactions which are present, which are required to stabilize this response, will not cause rapid thermalizations. So as was kind of described yesterday by Marcos, so generic kind of many-body systems, once you turn on strong interactions, would actually generically thermalize very rapidly. So we will be looking for systems which do not undergo this rapid thermalization, because then there would be no stable order, right? So these are these two conditions. Okay, so that's kind of that's a basic concept of this discrete time crystals. So maybe before now I will talk about how we actually implement these discrete time crystals in the experiments and how we can use it. But maybe before we go on, maybe let me slow down and ask if there are any questions. Does everything make sense? Yeah.
What is the distinction between this and a high Q oscillator? A frequency half of.
Okay. So, well, high Q oscillator would generically respond, would not have this subharmonic response if it's a linear oscillator. The linear oscillator would not have this subharmonic response. Exactly. So there is actually an interesting kind of question. What if you have a nonlinear oscillator? Then you can have things like period doubling, for example, which are kind of well-known phenomena in a classical physics. So and they are indeed very closely related. So there is now some actually kind of still active work to try to understand the connections between these two things. But I would like to kind of maybe point out one thing, is that we would like to talk about here the systems, quantum systems, which are truly isolated. So usually, if you have for example, driven oscillator, nonlinear oscillator, which undergoes period doubling. So to make stable, you need to have some kind of damping mechanism. So, but kind of on a general terms, what you need is you need to have, if you drive the system, you need some way to dissipate energy, right? So we are interested now to look at truly quantum isolated systems where there is no need for such a damping. And one consequence of that is that, you know, in such kind of quantum systems, you can stabilize the states, which are, for example, quantum superpositions, like a cat states, right, which clearly would not be possible in this kind of classical regime, right? And so what makes this kind of phenomena somewhat non-trivial is that despite the absence of this damping, the system still would not absorb the energy or would not absorb it very fast, right? So usually this kind of non-classical nonlinear effects are a combination of driving, kind of damping, and nonlinearity. So here we don't want to have this damping, you know, and that makes it somewhat special. It's a very good question. Any other questions? Or are you guys here all experts on time crystals already? Okay, anything? Okay, so let's go on. So I would like to now talk about the experimental system in which we implemented this such discrete time crystals. And the system I will be talking about today involve atom-like impurities in one wideband semiconductors, so in particular in materials like diamond. So these impurities are usually what gives diamond its color. So diamond kind of, you know, clean diamond, you know, would generally be, you know, extremely, you know, transparent, will not have any color, but, you know, sort of to have a color, you will have to kind of create some imperfections in these crystals, and they, you know, these imperfections often have some kind of optical transitions. They are kind of they fluoresce, and that's what gives diamond a color. So those defects are now explored in many experiments. They can be thought about kind of like artificial atoms. And I will elaborate on that in a second. And, you know, they, as such, you know, they can be used for things like, you know, for building quantum computers, for building biological sensors, and for this kind of many-body physics experiment, which I will describe. So basically, to create this kind of impurities, what you would like to do, you'd like to usually start with the material which is extremely clean, and diamond has a few unique properties. For example, it's very hard, it's very wide band, and it's actually a very high thermal conductivity. And you can now have the crystals grown, basically single crystals grown artificially in a chemical vapor deposition process, you know, or you can start with this kind of diamond powder, which are so-called diamond nanocrystals. And so basically inside this type of materials, you can actually introduce defects by, for example, bombarding these kind of diamond samples with with nitrogen ions. And, you know, one of the kind of perhaps the most useful is so far impurity in diamond is so-called nitrogen vacancy color center. So it's one of the many stable impurities, and essentially it involves a nitrogen atom which substitutes carbon atom in a diamond lattice and awakens a kicked out carbon atom. And basically this is, you know, becomes like an extremely localized point-like defect. And this defect can be thought about as a kind of, you know, artificial atom. Right? So I talked yesterday about real atoms, but, you know, if you start, for example, and, you know, the way how we detect these atoms is by just taking picture, by looking how they fluoresce. So the same thing can be done here. Specifically, if you kind of look at a reasonably clean diamond sample under the microscope, then what you will see kind of bright spots like this, and these bright spots, you know, could be some like stars and Princeton at night, you know, if the sky is clear, but actually they are not. They are individual defects, and you can basically verify that by just zooming in and doing spectroscopy, optical spectroscopy and microwave spectroscopy. You can really verify that these are single, the so-called single color centers. So these color centers, this in particular is nitrogen vacancy centers, so they can be detected optically, but also they have another important feature. So they have non-trivial spill properties. So in particular, in the ground state, they feature non-zero electronic spin. It's actually a spin triplet. There are 3 states. And you can rotate these spins by applying microwave fields. But at the same time, you can polarize the spins. You can initialize a spin in one specific state, in a 0 state, by shining light on these crystals, shining green light on them. And what happens when you shine green light, these NV centers fluoresce. That's what the image here shows. But actually, it turns out that they fluoresce differently, dependent on the specific orientation of the spin. So if the electron spin is 0, it turns out that excited so-called cycling transition. So basically, you see a lot of photons. But if the spin state is 1, then actually NV center is a lot less bright. And so you can use it to basically detect, to measure kind of orientation of the spin. And quite remarkably, this spin degree of freedom in this kind of NV center is actually extremely well isolated. So even under ambient conditions at room temperature, these spins can feature millisecond coherence times, right? So which actually for solid state system is quite remarkable. So okay, so we'll make use of these spins. So in fact, we will be looking at ensembles of these spins. Will be strongly interacting with each other. But throughout the process, we will use light to spin polarize them, to prepare, initialize them in a certain state, and then also read out their orientation. So last but not least, I should mention that these nitrogen vacancy centers, as well as other defects, can be actually created in nanoscale structures. They can be created kind of artificially. So, for example, if you start with a clean diamond and implant these color centers by just sending, for example, ions, shooting ions, so you can create these kind of arrayed structures, which maybe look a little bit like atom arrays, which I was showing to you yesterday. With one exception is that here, of course, you already see that these are intrinsically disordered structures, right? And as opposed to atoms, where we can just take a picture of these atoms, and if we don't like the orientation, we just can rearrange them in any way you want. So here is actually this is quite challenging to do, kind of this disorder, both in position of NV centers, but also kind of in their frequencies, and their transition frequency will be kind of central to the stock today. It's actually, it will be a feature in some way. Yeah.
So you say disordered, but the dots at least look somewhat periodic, like pretty periodic to me.
That's right. So here, okay. So here the attempt was to create a regular array. And actually, first off, this length scale here, these guys are separated by quite large distance. So at this distance, they would not interact with each other. So you need to reduce the distance by like a factor of 1,000. But even then, what you see is that this attempt to create this array was not very successful. There are few, which are, and actually, there is a lot of work now to kind of improve this, this situation, kind of basically reduces disorder. But we'll also tell you about how maybe we can make use of this disorder, right? How we can turn things around. So these are kind of current efforts that this community is broadly exploring. So people make use of not only electronic spins, but also proximal nuclear spins to actually create quantum registers, to basically manipulate, to create some small kind of processing units. Nuclear spins can be used to store quantum information. They actually can be very long-lived. They can live for seconds, even at the room temperature. So then there is an effort to kind of scaling up, to couple these impurities to each other. And here this problem of disorder is kind of very important. So on one hand, it kind of motivates one to think about, defects, different types of defects and different ways of creating them, such that you actually can create the ordered structure. But but at the same time, one also should be thinking about, can one really control disordered systems? So what if your disorder is something that you have to live with? Can you still do something? Can you guide coherent evolution of the systems? So there's a lot of effort to kind of also couple these NV centers at long distances. In fact, they have been used to make, to violate Bell's inequality over length scales of kilometers. And here you use this NV center electronic and nuclear spin as a memory and photons to carry quantum information. And finally, these NV centers, these color centers, can be used for nanoscale sensing and imaging. And if I have a little bit of time at the end, I will talk about that, and I'll talk about the connection of that with time crystals. So a lot of efforts now are addressing this problem. So actually here in Princeton, so Jeff and Natalie are here, they're actually starting, their own research groups, kind of addressing various, various aspects of this kind of research. But today I will focus on this particular thing, which is related to scaling up, related to this problem of disorder. But instead of trying to actually, improve the fabrication methods, I will try to ask a question where we can control this disordered system in some way. And this time crystal will be kind of an example which we will be using. So specifically, kind of the experimental system that we will focus on will be the system which has a lot of these defects. So in fact, we'll work with crystals which have such large density of these defects that the diamond starts literally looking black when you illuminate it with the white light, right? So it loses its transparency completely. And so in this case, you basically have a very large concentration of defects, and this defect will be dominated by one specific type, this so-called NV center. And in this case, NV separation will be, on average, will be about 5 nanometers, which translates in very strong dipolar interactions between them. And this is the dipolar interactions which we will be using. And so in our experiments, we will actually excite and measure about 1 million of NV centers at once. And such a sample, features a lot of disorder. So on one hand, the position of these NV centers will be random, but then also there will be other impurities like nuclear spins, kind of nitrogen impurities, which actually all will project some kind of random magnetic field at the point of each NV center. And so, for example, here, if you just make kind of conventional ESR spectroscopy, if you measure a spectral line, so what you find is that this line is actually very broad. It's actually maybe 1,000 times broader than that of the individual NV center, and this is really due to a combination of interaction between NV centers, but also due to kind of this disorder, due to this random field. So okay, so I mean that's kind of sample. Of course, to begin with, looks like complete mess, right? So you have to do a lot of work to kind of characterize. But actually, we were able to do it, and actually it turns out that, basically, at least for purposes of today's talk, the spin dynamics in these samples can be described by this relatively simple Hamiltonian, where you have some driving term which can flip the spin. You have some detuning of the field, which will be actually, we will have some random component to that, and this is due to this local magnetic field, which will perturb the position of this NV center. And then there will be these dipolar interactions. And dipolar interactions we will use to basically stabilize, for example, time crystalline response. So so this is how this actually sample looks like. So I told you that under white light it's black, but actually if you shine green light, if you start exciting this NV center specifically, it actually turns bright pink, because bright pink is where the emission of this NV centers happens. So that's how we know that there are a lot of these NV centers. So this is actually kind of an experimental team. And maybe kind of just before I conclude this kind of introductory part about the physical system which we are using, let me just show you an example of one experiment which we have done with the system, which actually shows that this kind of system can be used to probe thermalization. And the experiment is of the following kind. So suppose that we start with two distinct groups of NV centers and prepare them in the opposite orientation. So the way how we can do it is because it turns out that in a diamond crystal there are so NV center can be kind of oriented along 4 different kind of crystalline axes. And basically what we can do, it turns out we can actually address these groups individually. So we can, for example, prepare one group in a state up and another group in a state down. And what we can do then, we can just try to look how these groups interact with each other and how they relax. And what we observe here is that this kind of relaxation exists, but it's typically about 100 times slower than typical kind of characteristic spin exchange between these two groups. And moreover, these two curves are actually actually done under slightly different conditions. Basically, effectively, the disorder for the red curve is actually larger than the disorder for the blue curve, right? So, and basically, what it shows is that disorder here plays a big role. And so this actually kind of the physics of that is the following. So if you prepare these two groups and they, and you ask a question, so how fast they will exchange the excitation, of course, what happens is that, like if they're in resonance, then this exchange will be very, very fast. But actually in practice, if there is a disorder, then, they are not, most of them are not in resonance. So they have to basically find a nearby resonant pair. And then, this process of thermalization will depend very sensitively on the type of interactions that they have between each other. For example, in particular, they depend on the power law in this kind of, whether it's 1 over r cubed, 1 over r to the 4th, and so on. So it's actually, whether such system, thermalizes or not, in fact, depends on whether the interaction is effectively short range or long range. And this kind of will bring us to kind of very important topic about, involving, this kind of long range kind of thermalization in the systems with long range interactions. So I think Rahul will kind of devote maybe a lecture tomorrow, especially to that. So I want to just give you kind of a maybe a very short preview. So basically, it turns out that when the interaction is 1 over r cubed, the system kind of lies precisely on a boundary between kind of thermalizing system and what's called localized system. So basically, if the interaction here is very short range, then you might have a situation where this spin exchange, this relaxation does not proceed at all, because simply one of these atoms just cannot find any nearest neighbors to flip-flop. And at the same time, if the direction is very long range, it always finds flip-flop. So it turns out this 1 over cubed is precisely in between these two regimes. And one can actually describe this, at least in a kind of single particle picture. So when you have just one spin which tries to relax to above of the other spins, by using something which is called resonance counting argument. So kind of the idea is basically is the following. So suppose that you want to find a spin, blue spin to which this length speed can relax, and our resonance condition tells us that the two energies of them should be within this kind of dipolar spin exchange interaction. So in practice, if you have certain width of the distribution of energies, right, you will have only kind of a small part of these NV centers kind of being in resonance. Now you should go back to kind of your spatial picture and ask the question is, for example, if you want you ask a question, what's kind of a survival probability, what's the probability that the spin will not flip, right? So, and you can kind of now draw some radius around the central spin and ask what's the probability that, for example, there is no resonance within the certain radius R, right? And that's actually that's what's called resonance counting. So it's actually very easy to find this probability. It will be given by something like this. This is where this is just basically a number of the targets, basically, and this is a fraction to which you can actually flip. And what you see is that there is a very subtle interplay here between this, r cubed, between r cubed decay of the interaction and of this element of volume r squared dr, right? So basically, if this interaction decays, fast enough, then when you kind of convert this product into kind of the integral will converge. And if this R decays very slowly, and then it will not converge. So it actually turns out when this R cubed, here when interaction is 1 over R cubed, it's right on the boundary of this kind of converging and non-converging, and it's actually, in this case, you can kind of estimate this product as it will be proportional to this R, to this kind of element of volume, which we are looking in a power where this power law is disorder dependent. And if you then convert basically time and distance with this relationship, what you will see is that this kind of analysis will predict that the survival probability will decay as a power law, but with the disorder dependent exponent, right? And this is a signature of the so-called critical regime. So the system, in the sense of like localization, is neither localized nor thermalizing. Well, it's actually thermalizing, but thermalizing very, very slowly. And that's a feature of these specific dipolar systems. So that's a feature which we will be using. Yes.
I just want to make sure that I understand how this model is valid for the system.
Yeah.
So you have all of these other sites in between
Yeah.
these impurities, right? Where
That's right.
there are some dynamics, right? Because
That's right. That's right.
there are
Okay. So the question is, this is evidently a single particle model. So this would be, correct if we just created one spin impurity, in a buff of all kind of spin downs. And it's actually not really clear, whether it will really describe our system or not. Specifically, in our system, we'll have the same density of red guys and blue guys. And what will happen is that eventually these red guys will start competing for sort of neighbors where to jump. So there could be certainly some many body aspect of that, and the answer to this question is, yeah, this is a very simplified model. So it's probably dynamics probable, but, to say that, if you start with both red and blue guys polarized, and initially it should actually describe the system reasonably well. But as the time proceeds, there should be some deviations. And indeed, that's what we observe experimentally. But at least for short times, it's actually kind of an okay model, but we will see also some corrections to that. And these corrections are very important. And actually, in fact, these corrections go to the root of this kind of important questions. For example, does the system with long-range interactions thermalize, or can it be localized, and how? And this completely open problem now. And maybe Rahul can say something. Will say something, smart about this tomorrow. But this is where So basically, part of the reason why I give this example to you is to maybe to guide a little bit of intuition. But it's certainly not it is certainly not a good model for a system, certainly at a long times. Yeah.
Is this exponent correct, or is that just approximate? 4 pi over 3.
Yeah, this is for a single particle problem. You can just solve it, and that's
exactly the answer.
And that's the exponent that you give a few sort of. Right. So let me kind of pause. It's actually maybe a good time to pause and also ask if there are any questions about the experimental systems that we are studying. Right, so not only about this theoretical description, but about NV centers and their properties. Yeah.
The dipole-dipole interaction, is
Yeah.
that because the nitrogen is charged, or is it photon mediated? Or?
No, so this dipole-dipole interaction is just direct magnetic interaction. So each of these guys has spin, and spin has a dipole moment, right? And basically, because it has a dipole moment, it projects magnetic field at the position of another NV center, and that's what causes the interaction. And this interaction has, well, here there is a spin exchange, but there is also Ising component, of course. Right. Yeah.
So this picture only looks at disorder from other NV centers. Presumably, like the presence of other nuclear spins and such doesn't change the picture too much. Or?
So okay, so in this, so I might, qualifying remarks about, the validity of the single particle picture, but from the point of view of, let's say, regarding nuclear spins, what they will do is that they will just shift the frequencies of these different centers. And of course, one important component is that, whether the shifts are, static or they are time dependent. So this would make a big difference. Actually, to a leading order, this, the nuclear spins, for example, evolve very slowly. So the shifts will be static. But of course, in the long time, once again, there will be some dynamics, and this will modify this picture also. All right, so, okay. So if there are no further questions, let me go on and talk about kind of using the system to implement these discrete time crystals. And so basically in these papers by Vetica and co-authors and also by the Station Q group, they actually gave a prescription. They not only sort of pointed out, that these discrete time crystals can be realized, but they also provided a prescription for how to realize them. This prescription involved basically applying a sequence of periodic unitary. Each of them consists of the rotation of the spin around the kind of x-axis, followed by application of this interaction Hamiltonian, which basically kind of, as this name suggests, should correspond to many body localized kind of phase. So it's basically this Hamiltonian has some interactions, this Ising interactions, but also has some kind of random field components associated with that. And basically, what these papers argued that this kind of the combination of these interactions, should produce the kind of this, in that case, 2T periodic response. And basically, the key features that they pointed out is that this kind of response should be robust with respect to imperfections, and it should be long-lived because of the nature of this Hamiltonian. This is a so-called MBL Hamiltonian, which kind of does not allow the system to thermalize. So in other words, there should be no heating due to many body localization. So let me kind of a little bit maybe demystify this kind of protocol here, and I will do it by using a block sphere. So how many, I hope everyone knows what block sphere is. Otherwise we'll have to restart this lecture from scratch. Do you know what block? So is there anyone who doesn't know what block sphere is? So block sphere is a kind of a representation of the two-level system or of the spin. And basically it corresponds to spin pointing up, down, X and Y are basically coherent superposition of the spin state. So basically suppose describe this kind of the idea of this experiment. Suppose that initially our spin is pointing in the x direction, and suppose you apply now a sequence of pi pulses, which basically say rotate you around y-axis. So if these pi pulses are perfect, then one pi pulse will turn the spin into x, into the minus x, and then the second pulse will bring it back to x. And what you see in this case, in principle, you have this kind of 2t periodic response. So you need to apply two unitaries to bring your spin back. But of course, if you have an insulated spin, this response will not be robust. So for example, if you under-rotate your spin a little bit, and then you under-rotate it again, you do not come back to the same place. And so what it means is that, like in your periodic response, it will not be perfect. So there is like a phase slip, which eventually will basically, dephase your kind of oscillations. But so it turns out that if you add interactions, then they can actually modify this trajectory. And specifically, if you add a kind of appropriate interaction Hamiltonian, what it can do, it can somehow close these trajectories by, so for example, if you here under-rotate it, but you leave your system to evolve, it kind of evolves in a way due to this kind of interaction Hamiltonian, which allows you to basically close this trajectory. So, and that's kind of the basis, intuitive basis for this kind of time crystalline response. So in that case, the combination of this rotation, even if it's imperfect, but the rotation and this interaction might result in 2t periodic motion. So once again, we'll be looking for systems where have robustness to imperfections due to the strong interactions and no heating. So, and this is pretty much exactly how we have done this experiment. So in this experiment, what we do, we, polarize the spin, we start sending a sequences of pi pulses, and then we interrupt the sequences with this interaction period. I will explain you a little bit, maybe in more detail, what we do actually during this interaction period. We're trying to engineer interactions a little bit, and I will explain how we do it in a second. But what we can do, we can actually vary, for example, the duration of this interaction period. So, for example, if this interaction period is weak, but the pulses are perfect, so we see this up, down, up, down, up, down motion, and actually there is in a Fourier transform, there is this response at half of the at half of the fundamental frequency. However, if these interactions are weak, this response is not robust. So specifically, if we change this rotation angle a little bit, then what we see is precisely due to this phase slip, these correlations decay, and if you do a Fourier transport, and what we see is that this kind of, the peak is now no longer at the center, right? So you basically create this kind of two new components. But actually, it turns out that you can fix it with this imperfection by increasing the duration of interaction. And if you increase the duration of interaction, you actually restore this this central peak, and moreover, with longer interactions, even like the kind of a lifetime of this up down, up down, up down, this kind of subharmonic response is even longer than in the case when you have short interactions, even with the perfect pulses. Right? So all pulses have some intrinsic imperfections, which actually this approach can kind of circumvent. So basically, what we observe here is that the interactions can stabilize this 2t periodic response, which actually is a kind of what you would like to see for this observation of time crystals. So one can also do other experiments, and one can try to characterize the lifetime of this discrete time crystalline order. And one thing what you can do, you can just kind of look at this, peak intensity at a kind of different, after a different number of applied pulses, And basically that you can just look at how essentially how this kind of intensity of this peak behaves as a function of where in a sequence you are. And what we actually observe, kind of a non-trivial feature that we observe here, is that there is basically this peak height, which is like a kind of a order parameter here. It initially decays, but then this decay slows down. So there are these two characteristic kind of decay times, and kind of what is actually important is that this kind of second, especially the second characteristic decay time, does not depend too much on the imperfection in the pulse, so long as this imperfection is not too big. So if this imperfection becomes very big, then what you see is this decay becomes very fast. But if the imperfection is relatively small, then this decay doesn't really change very much. And actually, this is illustrated here. So, for example, if you plot this decay rate as a function of these imperfections under rotation or over rotation, what you see is that there is a kind of a plateau, and this plateau, the fact that it's not zero, it depends on kind of coupling to the environment and something like this. But basically, of this kind of small, kind of under or over rotations do not really change the kind of a lifetime of this order. And so like that means that this order is in some sense robust. So okay, so let's now try to understand what is kind of going on. So actually the precise sequence which we use is shown here. So this is the microwave pulse around the y-axis is a pulse which we use to induce these rotations which are close to pi. Actually, during the interaction period, we don't leave the system, in this case, to just evolve. We actually apply the so-called spin locking sequence. So we basically apply microwave pulse in the y direction. And actually what it does, it takes this complicated Hamiltonian and transforms it into something which is a lot more, a lot simpler, and actually it's a lot closer to what Vetica and coworkers actually suggested. So basically, by applying this pulse, what we do essentially, we average all of the terms in a Hamiltonian except for the interaction along the x-axis. So this is basically our effective Hamiltonian during this interaction stage, and this is our Hamiltonian during the rotation stage. And so basically, using this Hamiltonian, you can immediately see how this picture might emerge, because so what we do, we start along x-axis, and then we do this kind of rotation, and then around y-axis, and while the spins evolve, what happens is they evolve with respect to this Hamiltonian. And for example, this Hamiltonian, could think about it as providing an effective field along x direction. And so this is what spins do. They basically, in this period of free precession, they rotate around the x-axis, right? And they rotate in exactly such a way to find this kind of closed trajectories. So that's kind of like a little bit of a mean field picture of this time crystalline response. And using this kind of mean field picture, you can try to understand the phase diagram. So specifically what happens here is that, if you plot here, basically on one axis the rotation angle, so when the rotation angle is pi, everything should be perfect. And on the other one, you plot the period of this kind of free time evolution with respect to the interaction Hamiltonian. And what you see is that if this free time evolution is kind of very short, then you just do not have kind of enough interaction strength to close these trajectories. But if you increase this interaction time, then you allow your spins to precess around the x-axis in this kind of self-consistent field to actually stabilize the response. And these two lines are predictions of the mean field theory. And indeed, when this tau is short, what you see is this tau increases, the stability region. So this is a stable BTS phase. The stability region actually increases. So that's this mean field condition. So of course, what is actually also clear here that at a long time, this variational approach is no longer sufficient to describe the system, and basically, in fact, at the time when we observed this effect, we did not fully understand what is going on here, and this is connected to the fact that our system is actually, turns out it's connected to the fact that our system is not truly in the many-body localized regime. And so I still have 10 minutes? Right? So
15.
15, okay. So I think I will have time to explain. So now we actually have a picture of what's going on, and in the following I will try to explain. But maybe here, let me just pause here to see if there are any questions. Yeah.
So just like going back to the actual platform,
Yeah.
why is it that the triplet states are like so isolated in the NV centers, the defect centers?
So, okay, there are several kind of reasons for that. And so the main kind of, okay, the short story is that the main mechanism for which the spin would decohere is connected to phonons. And it turns out that, just due to the level structure, the coupling to phonons is just very weak. So that's a short story, but I can elaborate.
Okay.
And so, in fact, physics, for this reason, these experiments are done at room temperature. The phonon dephasing is much longer than any of these time scales. Yeah.
How do you turn on the interactions during the microwave, the Y microwave pulse, the rotation?
So yeah, so that's a very good thought. Okay, so basically I argued here is that, during this interaction period, I apply microwaves pulse with phase such as points along the x-axis, and that's where we have this kind of Hamiltonian. But then I said, well, then for rotation period, what we do? We just apply microwave on y-axis, but of course interactions will also be present. And so the reason why we can neglect it is that these pulses are much stronger and much shorter. Right, so it's basically much shorter on a time scale compared to interaction. But of course, the presence of interactions here will contribute to imperfections. Right? All right. So okay, so let me then kind of go on and try to kind of explain what's going on in this part of the phase diagram. And in order to do that, we actually need to derive kind of the dynamics of our system. So we will go now to the so-called toggling frame. So basically, what is a toggling frame is that, okay, so if our pi pulses are perfect, right, we would just kind of flip spins from x to minus x to x to minus x. And so let's just, go in a frame of reference, which kind of flips with every period, right? So then we can eliminate this kind of trivial flip, right? So in this case, if our pulses would be perfect, then to the leading order, all what we will have, and as our evolution is this kind of Hamiltonian, Ising Hamiltonian involving x-x interaction. And if we, in this case, if we, for example, polarize the spin along x-axis, it will not do anything. It's an eigenstate. It's a trivial eigenstate. But of course, our pulses are not perfect. And so this epsilon is this pulse imperfection, right? It's under rotation or over rotation. And I will describe this imperfection in this toggling frame as this term, which is a rotation along y-axis, times, to just remember the fact that this is a pulsed thing, this will be this sequence of delta functions. And now, so what I would like to do to analyze this Hamiltonian, I will do perturbation theory in epsilon. And I will Fourier transform this sequence of delta functions into into Fourier space. And basically, what you see here is that you can think about this periodic sequence of delta functions as as a kind of as a periodic driving, which is not sinusoidal, but have a lot of this kind of frequency components. And this omega 0 is basically an inverse of the period. So this excitation at multiple frequencies actually plays an important role, because it's a periodically driven system, so-called Floquet system. So here the energy is conserved up to a modular of this fundamental frequency omega 0, right? So essentially, what this means is that, due to this periodic driving, the system can change the energy in some units of omega 0. Right? The energy can be added or subtracted, right? That's because we have this periodic, external field which drives the system. And so what we can do now, we can first ask, okay, let's look at the effects linear in epsilon, how they will affect the system. But these effects, kind of linear in epsilon, clearly will be small, provided this first term is much larger than basically epsilon than epsilon tau, and that's actually precisely this mean field condition, right? This is the condition for closing trajectories, which I already have derived. So this kind of gives us, some boundary for phase diagram, but not a complete story. So in order to kind of do that, to understand, what's going on, we should go to a second order. And actually, in the second order, what happens is that, so if you look at this kind of Hamiltonian to a second order and perturbation theory, what happens is that you then now allowed to flip spins. This kind of term can flip spins in pairs. And actually, basically, if you work out the perturbation theory, so this pair flip spin process, of course, is proportional to epsilon square, but it also requires kind of the interactions to really, kind of fulfill kind of energy conservation. So basically, effectively, you end up with the system which we can, for example, take two spins which point along, say, x direction and flip them together to point along the opposite direction. And this matrix element here is you can actually just, calculate from looking at this kind of diagram. So it turns out that there are kind of two regimes which are which one can analyze. One of the regimes is when you have kind of short duration of this periodic of the period. In other words, large frequency, much larger than, for example, kind of a random field that each spin fills. So in this case, what happens is that this perturbation theory is proportional to epsilon square, but it also inversely proportional to this kind of disorder, for example. Disorder corresponds to this h squared. But actually, in the opposite regime, when omega is much smaller than h, what happens is that you end up just basically with this, kind of almost like continuum of all of this kind of Floquet states. So basically, at this point, what happens is that characteristic kind of spacing is not h squared, but is actually omega squared, and actually changes dynamics quite dramatically. So basically, so at this point, this is again a dipolar system. It interacts with this 1OR cubed interaction. So you can do this kind of resonance counting, which I described before. And this pair flip process will result in polarization decay, which will be kind of a power law decay. And then you can ask a question, for example, at what point does this, polarization, will decay by, let's say, 50%. And so this, because this is kind of a power law process here, actually it turns out that this kind of effective, decay rate, or if you want, time, will actually go into the exponent, and it actually will look like this. So for the short time, for the short duration of the time, what will happen is that this kind of the blockade period will appear in the numerator, but actually for the long time, when when the frequency is very small, what happens is that this combination of these two effects actually make this blockade period appear in a kind of in the denominator. And so basically, okay, so maybe it's kind of a little bit too kind of adventurous an attempt to explain it in 5 minutes, but basically this second regime where you're basically entering this this regime where the period of the driving is comparable to the disorder. So this is what actually causes this kind of stability diagram to kind of close, right? And in particular, so at longer T1, so you enter this regime which we call actually a critical time crystal, where basically you become more and more susceptible to imperfections. And in fact, this window closes as analytically it closes as a square root of t. But if you try to do this kind of numerically and kind of average over random positions, that's what that's how it looks like. And actually, it's really a very good agreement with the experiment. So basically, what we learned here is that this critical time crystalline order, what we observe is really very sensitive probe of quantum dynamics, and and particularly it really probes at this point. It really probes how system thermalizes. And so we actually, since when, really extended. We kind of made use of this idea, and we extended this kind of analysis to different types of Hamiltonians, which we can engineer dynamically. So this is so-called, what I talked about so far is so-called Ising discrete time crystals. So you can also create a Hamiltonian which doesn't only have Ising term, but also have spin-flop interaction. You can also even extend it to the Z3 order. And actually we studied this also. This is, for instance, the example where you have a 3T periodic time crystal. So in this case, what you do, you simply apply 2 pulses. So you just have the system interacting with full dipolar Hamiltonian, and you apply 2 pulses, which basically connect these 2 states and these 2 states sequentially. And so actually, what will happen, if you think about it. So for example, if you start here, what will happen is that basically, if you apply this pulse first, it will bring you here, right? And the second pulse will not do anything. Then you let the system interact, and you again apply, first this pulse and then this pulse, so it will bring the spin here. And what you see is that basically you end up like with a clock type, model. So and actually, it will give rise to a T periodic DTS, and actually for short interaction time, it's not very stable, but for long interaction time, it becomes stable. But actually, if you wait even longer, then, we see some, kind of very non-trivial dynamics where basically system kind of starts acting as a buff to itself. So actually destabilizes this disorder. So maybe this is something I can talk to. So actually, that's maybe the kind of, that's a phase diagram. So actually, these are for these 3 different kind of cases. And actually, this projector, what you see here is actually for small time, for small interaction time, this like this DTS is actually even more stable for the case of Z3 than for the case of the Ising. Actually, if you go to a long time, and this is actually the projector here, there's some shaded area. So in this shaded area, what happens is that these time crystals become unstable due to dephasing. And actually, I can maybe talk to you in the question and answer session. So I think I should actually finish, but let me just, as a kind of finishing touch, let me tell you a little bit about kind of new direction which we are pursuing. So you could ask, okay, so these discrete time crystals, I mean, it's a kind of cool concept, Maybe it's, different from classical nonlinear systems, maybe not, but really who cares how this can, what can it do for humankind? Actually, it turns out that the answer, it turns out that there might be actually some real world applications of this effect. And it's connected to the fact that, a lot of the, basically, the things which we are doing as physicists, kind of the tools which we develop, then end up being useful in other areas. So, for example, these are the kind of the short list of the tools which kind of originated in physics, but it kind of transformed areas like biology, medicine, and material science research. And this all basically goes from 18th century to 20th century. Right? So it actually turns out that this kind of systems, like for example atom-like impurities, spins, can actually also be applied in this area. In fact, they can be used as a very sensitive probes of localized fields. So, for example, if you have a small molecule, such as, for example, a protein, then these molecules consists of nuclear spins, and these nuclear spins, they actually they produce magnetic fields. And so, for example, if you take one of these NV centers and bring it close to one of the of those molecules, it turns out that you can actually sense magnetic fields produced by these different nuclear spins. And the reason for that is simply that the typical dipolar fields actually scale like 1/r³. So if you come close, with your probe, you can actually measure fields from very small objects, like individual nuclei. And this kind of idea allows one in particular to take kind of bulk magnetic resonance imaging kind of systems and really scale it all the way down to the point where these NV centers can actually just do MRI on single molecules or on very small objects. But the way how these things work are actually there is a little bit kind of more involved, and in particular, so in this molecule there are maybe there's a million nuclear spins, right? And these nuclear spins they all kind of precess at various frequencies, so you end up with like a lot of kind of a mess, right? Basically, you end up with magnetic noise. So how can you really distinguish, isolate, address individual nuclei? And actually, the way how to do it is to basically use this NV center as a kind of spectrum analyzer. And the way how you do it, you typically apply to do the sensing experiments, you apply a sequence of pulses, maybe thousands of pulses, where basically, what you try to do, you essentially try to synchronize the motion of your spin with the kind of target which you try to kind of detect, the target of interest. And so specifically, by applying this pulse, you become sensitive to just one specific component, right? And actually then you can isolate this component, zoom in and probe it. And that's kind of the idea. So using this idea, one can do NMR spectroscopy of single proteins. So you can, make measurements in living cells. You can actually look, for example, in material science, you can look at systems like this, atomically thin materials, and you can basically do MRI by just peeling these materials layer by layer, and you can really start looking at shifts, basically, which when once this material becomes single layer. So these are kind of the cool things which we have done over the last few years. Okay, so now you can ask, okay, what's the relationship of that to time crystals? Well, it turns out that in all of these kind of sensing experiments, there is always kind of a fundamental limit to the sensitivity which you can obtain, which basically is related to the product of the coherence time of these sensors and the density of the sensors. So basically, to improve the sensitivity, you would like to put a lot of these NV centers very close to each other. That way, you can improve your signal to noise. But actually, what happens is that in practice, this you cannot do it because these NV centers start feeling each other's presence, right? And basically, instead of measuring the field from the target of interest, they measure the field from each other. So it's actually at this point where this kind of time crystal type protocols can actually help, because as we already have seen, in time crystals we can actually use interactions to really lock spins to kind of make them response in sync. And it's precisely what we need if we would like to kind of measure, do these precision measurements. So in particular, these time crystals can actually not only kind of reduce this dephasing, they can actually also stabilize these kind of non-classical states, which can be kind of very, very sensitive, probes of these external fields. And so, kind of we and also others are kind of thinking about how to use it, and there is actually, we have a specific kind of proposal paper how we can use this discrete time crystalline type states for precision measurements. So I think this actually points out to another exciting frontier where basically this kind of many-body dynamics really, and particularly on equilibrium correlated matter can really be thought as a kind of, as an ingredient for, like, for example, the new generation of sensors. And that's kind of, another example of this type of thing which I advertised in the beginning of my yesterday's lecture. So this kind of, understanding of quantum matter away from equilibrium really is actually can be useful in the long term as for applications, and this is another example of that. Okay, so I think I've sort of used up my time, so I guess at least gave you a little bit of a flavor that we are really kind of our research in this field, we are kind of gaining the control over quantum world. So I think this actually at this point it allows us to study some very cool and interesting physics, and perhaps some applications of these techniques can be foreseen. So I think with that I should finish.
Any questions? Professor Lukin?
So in the time domain of the time crystal data, you observe a fast and slow exponential decay.
Yeah.
Is that somehow related to the idea of pre-summarization?
Well, that's a very good question. So kind of, so probably not. So that's a short answer. So kind of pre-formalization is, is a phenomena which would occur, for example, if you have some, kind of approximate conservation laws or something like this. So this actually is not the case in our system. So what we believe, what happens is that basically, so we, like when we start, kind of, let's think a little bit about in this mean field picture, right? So we start with perfectly polarized NV centers, but then, if you really want to have a stable trajectory, your state, your effective polarization should be adjusted to the point where it actually closes this trajectory. So basically, this fast time scale, we believe is this time that it requires for sort of initial, polarization to kind of relax to some value, which is kind of quasi-steady state. And then that's what is kind of, the final decay is a decay of this kind of steady state. But it's actually, it's not, at least, there is no obvious kind of pre-thermal, behavior in our system. But instead, what we believe is that this kind of long time decay is really, is connected to this slow critical thermalization.
I guess in this 3D system, you have this critical dynamics, which complicates some of the analysis. And can you just study this in 2D?
Yeah, that's, this is something that we are kind of thinking about and working on. So there are two kind of approaches which we are exploring. One of them is basically applying kind of a very strong gradient, which kind of isolates basically one layer in this in this three-dimensional system. But there are other also examples. So for example, like the surface of diamond has some impurities which we don't completely understand what they are. Maybe Natalie knows. It's the one person in the world, maybe the best person to talk to. But basically one could, for example, think about this as a two-dimensional system. We're kind of looking a little bit at that system. One could also use, for example, this experiments I showed you where we now probe nuclear spins in boron nitride. So one can create a truly two-dimensional nuclear spin system which one can explore. So that would be very interesting. So yeah, so there is, maybe Rahul will comment on that actually. So from the point of view of single particle physics, such systems should be many-body localized, but actually from the point of view of many-body physics, it's actually not clear. And that's maybe would be one interesting thing to explore.
Let's thank Mr. Lukin again for we'll take a short coffee break and be back in 10 minutes.
They wrote that. Yeah. So in the document, I mean, you're fine, but in the document they said that you'll prelim by your fourth semester. They're moving up like this RA or if my lectures came after fourth semester. Yeah, but working. I guess I think I hope that. That's the new change phase. And